We're very excited to have a guest lecturer and a guest speaker, Michele, who graduated from Stanford a while back and is back today to give us a talk. He's from Replit, and he will give his own introduction so that I don't miss out any.
Hi guys, feels good to be back at Stanford. I think the last time I gave a lecture here was 2020 during the pandemic, so there's been a few years. The intro has pretty much everything. The only detail to add is that Akanksha and I overlapped at Google for like a couple of years. We worked on Palm and Palm 2 together, and she kept training amazing models. I went to Replit to start to build agents. And this has been my professional obsession for kind of a decade at this point. I started to do representation learning on code when transformers just came out. Then we trained LLMs, and I took care about the code gen part of them. And now I'm very excited about building agents on top of models. So the goal of today is I want to show you how fast the field evolved in the last year and how we've been building coding agents in a completely different way during the past basically 12 months. So starting from there, the first step is we went from basically building copilots, that has been like the hot product in AI for a couple of years, all the way to creating agents. So we started with autoregressive code generation models. That's when the first GitHub Copilot release happened. And then we created slightly better models that were capable of following instructions. So in that case, rather than just completing the code for you, you could be asking a question in natural language, and the model gives you back an entire file generation or multiple files. And this is around the GPT 3.5 era. Then we saw another big leap in terms of performance with the latest frontier models. Basically, they started from GPT-4, and they were capable of doing repo-level code generation and understanding. You could build on top of these models some level of long horizon tasks, so split into multiple steps. And last but not least, we started to see tool usage and computer use. I'm sure you covered both these topics during the previous lectures. I've been snipping your syllabus, so I'm not going to go into detail exactly how they look like. But the North Star here is that the more models improve their capabilities, the more eventually every agent builder will love to hand off all the responsibility over to the models without writing much code around it. So the ideal world is, at the limit, the user expresses their intent in natural language, and the model does everything else. We're not there yet, so what is the interim solution that we use today? This is how a coding agent looks like. I think it's very similar to what we've been seeing basically since week one. And it's a system that is capable of dynamically directing processes and tool usage, but it still maintains control over how they actually accomplish the tasks. So even when we reach the very end of this lecture, we're going to basically keep seeing a system that very much looks like this. There is a human that gives the input, we do LLM calls, and then there is an environment where we take actions, and there is a feedback loop. Now, why is it interesting specifically to do this with code? I think code comes with a bunch of additional properties that make life more exciting when building agents. Namely, the fact that we have a lot of tools that we built in the last decades on how to analyze code. We know how to do static analysis. We know how to compile, interpret, and execute code. So there is much more richness in terms of signal of what we can get out of that feedback loop. And I don't think it's not going to come as a surprise to you that agents kind of started from code. Like the first exciting applications of agents that we've seen in the industry, they started from here. And in a sense, I feel code always predates almost every other capability. Like we start to take a new generation of models, they get pushed as far as it gets on code, and then we find other domain areas. But I know I'm very much biased, but to me, like the most exciting applications of agents today, of course, is still revolving around code. And so like any field, you need evals to understand if you're making any level of progress. So Copilot started with a different set of evaluations. Back in the days, we had human evals, MVP, MVPP, and so forth. Those evals are really focused on generating code segments, but they're very limited in scope. So that on the right, you see an example of what human eval looks like. You were basically getting a method signature, doc string, and then expect the model to give the implementation. The implementation usually was most of the times a one-liner. Another issue of human eval back in the days was the size, the sample size. It was 164 samples in total, so a very limited benchmark. That being said, it's important to remember that in our field especially, usually evals always precede capabilities. Think of what happened with ImageNet. ImageNet was a massive effort that started at Stanford in the early stage of the previous decade. And the moment that benchmark was released, then a lot of different groups started to slowly climb it over time. And it took several years basically to completely saturate ImageNet. We have seen the same with human eval. When the first codex model came out, it was like in the 20% or so. Right now, if you check the latest papers about the frontier models, they even stopped using human eval almost. You see the scores there are in the order of like 95%. So it's kind of saturated. It doesn't give a signal any longer. So it kind of comes natural now that there has to be also a counterpart on how to evaluate coding agents, right? And of course, that benchmark already exists, and that's what everyone in the industry and academia is using. The benchmark is called SWE-bench, and the task here is you generate a PR from a GitHub issue and a given code base. So what this group did a couple of years ago at Princeton, they took 12 open source Python projects. They carved out a bunch of PRs from those projects that could be tested with the unit test harness that was already available on the repo. And they created a lot of different examples. Now, definitely, this benchmark catalyzed a lot of progress in the last couple of years. And researchers, companies, everyone is rushing to ascend the benchmark. The good news is that it's still not saturated. I think the current SOTA on a subset of it, which I'm going to explain later, is around 60+%. So there is still some juice to squeeze out of SWE-bench. But hopefully by the end of this talk, I'm going to convince you why this is not the end game. Like software engineering is such a wide discipline and is not only about taking a description of an issue on GitHub and turning that into a PR. I think if you start your own like student projects for this course, you're probably not starting from a PR description. You're going to be starting from an empty repository. You're going to be discussing with your friends and colleagues, what do we want to build? And that's a completely different problem set. So we're going to get there, but it's good that we have something to start from and something to measure. Now, I think some of you in this group are also using SWE-bench already, and you probably stumbled on how hard it is to use it. I think the beauty of human eval, benchmark I showed you before, is that it was extremely, maybe it's a bit of a misnomer. It was very easy to run. You will just basically pass the prompt and then get back the code and then execute it on the fly. SWE-bench comes with a lot of burden in terms of setting it up. You have to basically create containers and you have to set up 12 different open source projects. So there is a software engineering challenge there. There is also another challenge on the quality of the benchmark per se. So it turns out that out of the initial, I think, almost 2,000 examples that they came up with, a lot of them had issues. Some of them have a broken harness, so it's impossible basically to run tests. Some others, and you can see this from the plot on the right, when asking software engineers to actually, professional software engineer to find a solution for some of those problems, it took them more than 4 hours. So someone specialized on that problem, the specification of the issue was so ambiguous that they didn't really know what to do. So it took them so many attempts even to figure out how to solve that. So it's kind of clear that when there is this wide variety of complexity, this is probably not the kind of benchmark that we want to target today. It's a bit premature to try to go for tasks that require several hours. So OpenAI, if I recall correctly, at the end of last year, they paid almost 100 software engineers to go through all the different tasks in the original SWE-bench dataset and filter down a smaller subset of it, which is called SWE-bench verified. And it basically solves most of the problems that we've been talking about. So it tries to remove the harder ones, it tries to remove the false negatives or the unspecified problems, and so forth. So if you go and check SWE-bench today, the one that you want to work on is SWE-bench verified, which is a bit more approachable. By the way, I forgot to say, I'm more than happy to take questions while I'm speaking. Let's make this interactive. I don't want to give like a monologue for 1 hour and then wait until the end. So just raise your hand and let's have a chat. Okay, so we set the stage. We talked about evals. We talked about why they're important. So it's time to start to talk about coding agents. So the first attempt, and probably like the one that kickstarted the field, especially in academia, is SWE-agent. It's based on React. I think you covered that also during week 1. So I'm not going to explain again what React is. but it was the first breakthrough result on SWE-bench. So initially, the first attempts at SWE-bench were literally tackled with taking the entire description of the issue, passing some of the coding context on LLM, as the model to generate backcode, apply to the repo, and see if we actually found the solution or not. As you can imagine, the performance there were abysmal. I'm talking about like single-digit % resolution rate. So the group here, again, is basically a subset of the people who also did SWE-bench. They came up with this core idea of finding specialized tools that you as a software engineer will be using, put them in a loop in a React agent, and especially finding the right interface between tools and LLMs. This is the core problem that they basically solve. So everything else that you see here on the drawing is very similar to the high-level agent description that I showed you before, right? You have an LLM in the loop, you have a bunch of tools. The computer is basically your environment, so you can interact, you can run terminal commands, you can write on the file system, you can read data. That's the environment to interact with. And then you can take actions, you execute the code, you find out if the PR you generated is correct or not, and then you make a decision if it's worth moving forward or not. In principle, it sounds very easy. That's pretty much how each one of you writes code when you're building your project. In reality, there is a key challenge, which in the paper they call ACI. So rather than doing human-computer interaction, here the problem is how you have an agent interacting with a computer. So agent-computer interaction. The reason why we have to find solutions to this problem is because you can't put the entire complexity of a developer toolkit in front of an LLM. You can't just tell a model, these are all the shell commands that are available, and these are all the files that are in context, and these are all the different tools and techniques you could be using. Now go ahead and make it happen. That is a pipe dream that we're going to accomplish whenever AGI is going to happen, whatever is the definition of AGI. Today, we're not there. So how can we make this more pragmatic and actually make it work in 2025? So first of all, the action that an coding agent can take, they need to be very simple and easy to understand so that the model doesn't get confused. And what I mean by that is even when you're invoking a tool, rather than having a very long method signature where you can pass a lot of parameters and each parameter has a high cardinality, the ideal world is that you have a method that takes a Boolean. Like it's very easy to invoke the tool and it's clear the model doesn't have to make too many choices when you call a tool. Let me give you one very easy example. Whenever you navigate your file system, the degrees of freedom you have in front of your file system are extremely wide. You could decide, to go depth first search. You could decide to do recursive listing. You could decide to take a lot of actions on the file system. If you tell the model, here is my file system, go ahead and do and perform task X. It will try to find, like every time, given the stochasticity of the LLM, it will probably find a completely different strategy on how to accomplish that task. The goal here is to make that so narrow and put it so much on guardrails that whenever you say you want to browse a file system, it will always do it exactly in the same way. So that also in the agent, in the loop, you can interpret the output of that command always in a very specific way. That is the insight of what it means to do proper ACI, like making the tool usage easy and the output as structured and as deterministic as possible so that the agent basically doesn't get lost in the process. And similarly, the other points are, for example, the environment feedback should be informative but concise. What do I mean by that? Imagine copy-pasting the logs of your broken web app into a model. They can be so verbose, and most of them could be so useless that if you keep doing that and basically keep expanding the prompt of a model, just throwing in there all the logs, eventually, no matter how smart is the model, it's probably not going to understand anything. And you as a developer, you kind of face the same issue, right? Like you clear your console, you don't want to see everything that happened in the last 10 minutes. It's just an overwhelming amount of information. So you have to treat whatever you're building with your agent with a very similar principles. So what are the,
Can you elaborate on how do you ensure that the agent's output is structured and determined?
That's a craft more than science, unfortunately. And it's a lot of trial and error, but you have some guiding principles such as pass the least possible amount of information to the agent. So if you know how the logs of your app look like, maybe you decide to pass only logs up to a certain level. Like you want to just pass errors and warnings. You don't want to pass him for debug and so forth. This is the simplest example I could give you. But there are a lot of opinionated choices you can do on your end that will determine basically how much information is put in context. I think a good follow-up question there would be, how do I know I'm getting this right? That's why I started from evals. It's not like an academic fixation. If you don't have a way to measure if what you're doing is pointing in the right direction or not, you cannot do a lot of byte-based development. That as much as it's cool today on Twitter, it's probably not the right way to make progress on agents. Any other questions? Yeah.
This looks like some form of environment that can be like completely sandboxed and so on, right? Well, is that true for the real world applications that you go actually deploy with Replit and so on? Like, is that assumption even true?
So that assumption holds for us at Replit, and I'll show you a bit the product at the very end, because every application you build is running in an isolated container. So we cannot know the boundaries of our world. The moment you want to do this in industry with like a real world code base, things are much harder. Like you might have a ton of microservices and everything has slightly different specifications. And that's why we haven't seen yet an agent that is capable of refactoring large code bases. It's probably like the most financially like amazing thing you could be doing with a coding agent today. You know, if you show up at a bank and you say, I'm going to take your COBOL code base and I'm going to turn it into Java. As boring as that sounds, it's probably you can cut any contract size if you're capable of doing that. But these problems are hard because of the basically open world assumption. Yeah, it's a very good point. Okay, let's go. So let's go through the building blocks, which we're gonna basically carrying over until the very end today. But the first time that they were enumerated, it was in the SWE-agent paper. And again, if you ever written code in your life, this should sound very familiar to you. Whenever you're attacking a problem, the first thing you want to do is you want to search the files that you want to edit. So if you have an idea that you want to change component text in your web application, then you're going to go and find them in your file system. Then you want to be able to view the files. And like in this case, the choice that they made was to have like a viewport, very similar to you, like opening VS Code. You're not going to be reading a very huge file, right? Your focus will be on a subset of a source file. Then you have a file editor, like literally the action of deciding, I'm going to change the code. So the diff that is going to be generated by you. And last but not least, and this is deceptively tricky, is how do you do context management? So how much information do you have to recall from the previous changes that you have made? If you ever embark into a refactoring task yourself, you know that, say, you change a class name and some method definitions somewhere in your code base. And you need to then find all the different instances where that class is used. You need to change the way in which the methods are being used. So how far back do you want to go in your memory? How much of the information do you want to keep? And that's the same problem that I've been repeating already a couple of times. You can't afford to pass the entire information that the agent has been seeing in the trajectory, because eventually the performance is going to drop dramatically. Let's go to the result. I already spoiled them before, but this was the first major, almost like step function improvement we've seen in coding agents. So we went from like single digit just by doing basic LLM usage plus RAG, all the way to 18% with what back then was the best model available, GPT-4 Turbo. And with they're running an ablation study here, so I'm going to show like in detail what allowed them to go all the way to the number. So this is the ablation study I'm talking about. And the reason why I'm trying to highlight it is not because this is by far exhaustive, or is also something that probably you wouldn't be doing today, because this is almost 1 year old at this point. Where I want you to put the attention is, again, the fact that you need to have a benchmark in order to make some of these decisions. So for example, I talked about the file viewer, right? And they decided in their paper to have a viewport of 100 lines. You might say, why not 50? Why not 200? Why not the entire file? And it turns out that 100 in their ablation studies was kind of the sweet spot. And you can understand why. Like if you always pass the entire file, you exhaust the context of the LLM very quickly, so you can't afford to do that. If you're only giving a very small chunk of the file, you don't even have the kind of like peripheral vision of what is happening. Like maybe you have a method definition, but if you have 100 lines, you also get the class definition. It's far from perfect. These are all heuristics. But again, like having an eval that you can run on the spot allows you to understand if you're heading in the right direction. Similarly, they show that how you should be doing search on the file system, how you should be doing file editing, and so forth. So some examples, I think maybe this one we can skip. Yeah, here the key idea is you could either try to rewrite the entire file, or you could try to edit in place. So you could try to generate a diff. And last but not least, if you can afford to run a linter and an LSP, you can basically statically analyze your code and find out if, say, you introduce a variable usage that has not been defined, or you're calling a method after you did the edit that doesn't exist. If you can run these tools rather than just modifying your code and execute it and hope that it actually works, you can immediately get a feedback loop and realize you should have basically asked the model, that method doesn't exist. I want you to go and change it, or I want you to use something else. So this list could be much longer. Like there are a lot of different heuristics you can use to make edits more powerful. And we're going to be talking about how edits are actually done today. It's even more advanced in this. Similarly, search. You could decide to basically open entire files. You could decide to do something like iterative search, where you find like a few instances, and then if you find out that they're not enough, you keep searching for more files. What worked best in their case was to do summarize search, which means they open all the relevant files and then they summarize the information about them. And think about it, when you create your own PRs, you don't have to remember all the details of the relevant files. Sometimes you need to know, okay, that class does X, and that's why I should call that method. Like you just need the high level of what something does. So that's the intuition. The LLMs are amazing at summarizing. You pass like a large code definition, and then they give you like a two-liner of exactly that does. So you can represent a file system basically as a set of one-liners of what each file is about. Now, why only 18%, right? It's a cool number. They definitely got a big bump up in terms of performance, but where was SWE-agent failing? And here you will see in the plot the following. On the x-axis on the left, we have the number of total steps, which is basically how many React loops we are taking. And on the y-axis, like how often this is happening. And it turns out that, if you see the oranges, which is the resolved PRs, there is a very big drop around basically 15 steps. The reason why that happens is, again, due to the context management that we were talking about before, and to fundamental limitations of an LLM. So let's dig into details there. What do I mean by that? First of all, there were some problems, especially back in the days in SWE-bench, before it was filtered down to SWE-bench verified. There were some problems that no LLMs could have solved. And there are still today some problems that even in the last state-of-the-art solutions, there is a good, say, 40% of the problems that LLMs still cannot solve. So of course, if you just let the LLM spin the wheels and keep trying, it will do as many steps as you want, but it will just keep failing. And at the same time, also, if you keep adding a lot of memories in context, eventually the agent becomes less smart, and then it's not worth to keep spending money. So maybe this was the first insight that was very useful for coding agents. If you don't get to the solution kind of immediately, especially if it's something that you are building as a product and you're selling, you can't afford to keep calling an LLM in the loop tens or hundreds of times. Like eventually it becomes prohibitively expensive, especially if it's not like an enterprise product where people are price insensitive. And as you can see, the plot on the right is basically strongly correlated because it's the cost of the solution. So there are some problems that requires tens of dollars, and it's questionable if at that point it's better to have a human solving them rather than an agent. So some of the failure modes that we have seen in the SWE-agent paper, definitely editing was one of the big reasons why. So by editing, I mean, not only sometimes the model is not capable of edit the files accordingly to create the solution, but sometimes it fails because it doesn't know how to apply correctly a change to the file. And I'll show you some examples, but the long story short here is that LLMs are not capable of generating diffs. This is the format that GitHub and like Git in general uses. LLMs are not going to output a diff that applies reliably to a file. So you need to find some workarounds to how do you express an edit. There also the problem of laziness. I'm sure if you ever use chatbots like ChatGPT, Claude, and so forth, you probably have seen very often, you make a request based on a file that you pass in context, and the model tells you should change these 2 lines, and then it writes a comment and it says, keep the code as it is, and then it writes some other lines of code. That is perfect for you as a human because it serves the purpose. It tells you what to do. You can quickly copy paste things and you can get your things done. An agent gets lost there. If you replace the content of a file with a lazy edit, which basically contains these comments, you break the application because it's dropping blocks of code that were actually useful. So that's another big challenge. And last but not least is they get towards a long horizon task. So the longer you let it run, the lower is the probability that they're going to be doing well. So for this reason, given that the top 2 issues that we found out are how challenging edits are, and sometimes like failing to correctly find the edit location or even the files that you have to work on, from here, I think the field got split into 2 different directions. One is more of a agentless solution. I know the lecture is about coding agents, but I'm going to show you something that is not actually an agent and it performs pretty well. And then the other direction instead is even more advanced and more, let's say, intricate compared to what I just showed you. So let's start from the easier one, which is agentless. And the idea here is LLMs since a while have been kind of augmented by not only the core model, but rather, also using retrieval on the side. I think that's what everyone calls RAG. LLMs can also do tool usage. And last but not least, you can have some level of memory management. So rather than blindly keep adding information to the context, you can have some logic under the hood that decides when it's worth to drop information from the prompt or if it's worth to keep it. There is no feedback loop in here, right? It's just whenever you do a call, you augment with additional information that will make the LLM call more effective. It turns out that when the first implementation of Agentless came out, with a very similar model, it went all the way up to 25%. This is interesting for several different reasons. The code base required to build something like Agentless is a fraction of what it took to build SWE-agent. It's a much simpler system to build. It's also much cheaper. Like we're literally not looping. We're not doing a lot of different React codes. I cut some, additional bars from that plot, but there is another version that they ran back in the days where they try to do like a fixed amount of retries. And even there, the additional performance improvement they got was like 1 or 2 points. So it wasn't even worth to run it. But it's kind of amazing if you think where we started from. We started from few percents based on just the model plus RAG. And then SWE-agent showed us where that the agent was failing, where the biggest challenge. And then part of the community decided, you know what, we're not going to build an agent. We're going to build the tooling on the most crucial problems. We're going to pass the right information straight to the LLM. And this is going to bring us very far, which is the case because basically they beat the SWE-agent SOTA back in the days. Now we can start to talk why editing is not easy. This is a refactoring task. So basically, it's a benchmark coming from Either, which is basically one of the groups that pioneered the agentless architecture. And here they're refactoring large chunks of code without basically skipping any instance to be refactored or making any mistakes. I'm showing this to you because I want you to look at how wide is the variance between models that are kind of seemingly in the same class, or like they were not released so far apart from each other. Claude Sonnet is definitely at the top, is crossing 90%. Surprisingly enough, it was performing better than O1 Preview, which is one of the latest reasoning models from OpenAI. But I think it's also more interesting to take a look at the long tail and how quickly it drops. So I think that there is often a misconception in the industry that whenever a new generational model comes out, they're all kind of equally capable on certain types of tasks. That couldn't be possibly more false. And once again, it seems like I'm trying to teach people to do research here. That's not my goal, but I can't put enough emphasis on why evals are important. This is not SWE-bench. This is a very small bespoke task, but it was very important for them to create it because they realized, okay, if I want my agent to do refactoring, this is the model I should be using. And there are models that are amazing at being chatbots. I think like if you use, GPT-4 Omni as a chatbot compared to Sonnet, you probably don't see much of a difference. But when you put them in front of a refactoring task or an editing task, the gap is extremely wide. This one is purely about editing, so it's small coding exercises where we try to add new code, on a small file. And again, even here, you can see something like CodeStral, which is a model that Mistral train focus on code completion. It has probably like a 30 points gap compared to O1. The second bar there is Sonnet precompiled as well. So like they seem to belong in a completely different league. I'm not going to go into speculation on why they are better. I think other people know much more than I do. Definitely, it's a combination of better pre-training, better post-training, and possibly like collecting a lot of high-quality data. But again, it's important to be able to have communities that are creating all these benchmarks so that we know exactly what is the best option to use at the right time. There is so much you can do in building a better scaffold for the agent, but if the underlying model is not capable of doing code edits, you're not going to be able basically to build a good agent. It's still the core intelligence is coming from the LLM, not from the scaffold. That's another view which I like over like the performance of models. And you can see that most of them have not improved at all over time. Like even if you take GPT-4 Omni, they had several checkpoints throughout, the last months. But some models have been climbing this skill, like the Quen models have been like climbing the editing capabilities over time because they put effort as a team to make them better on the task. Like GPT-4 has been kind of stable for more than a year. Sonnet had a bump during basically the V1 and the V2. And even for like if you ever decide to go down this path and start to build agents, even if they're not exclusively about code, it's important for you to remember that you might not be changing a single line of code in your system, and overnight you could be seeing a gap in performance, and that could be due purely to the fact that you're using a new checkpoint from whatever provider of choice you have. So if you decide that you're building your agent around the latest reasoning model from OpenAI, those models are not stable over time. They release new checkpoints, they always behave in a slightly different way, and you could see variations because of that. Plus, there is also the variation coming from the stochasticity of the model. Like every time you ask for exactly the same task, if the temperature is high, on some tasks that are simpler or trivial, the model performance tends to be always very stable. But on some other tasks where the capability is still less developed in the model, you might see a crazy amount of variance.
Yes. When you're sampling from the models, are you using temperature like that, like high temperatures? So that
high temperature.
That you care about. I mean, most of the evals that we do in academic settings are asset K, and coverage kind of thing. But like, can you say a little bit about what the real world looks like if you're doing evals?
The real world is usually high temperature, pass at 1 or pass at very small K, especially like the more advanced an eval, the more expensive it gets. An entire SWE-bench run, depending on like if you're scaling test time compute or if you're doing like a lot of loops, will cost in euro like several thousands of dollars. So depending on the size of the company or even if it's a research lab, you need to be cautious on how much tokens you burn for an eval. So I think the times of doing like past 100 on human eval are gone. Yeah, but that leads to the issue that there is a lot of variance, even just because of the high temperature. Most of the quick evals that like we try to do, say like on a daily basis to make short-term decisions, they tend to be high temperature, past 1, in the order of say hundreds of samples. If the gap is very small, I never consider it statistically significant for obvious reasons. But if I say like a 5+ points, then my vibe check tells me there must be something there. That's the harsh truth of building things fast. Okay, let's go to to diff formats. So that's what I was hinting at before. Most of the diffs that you see even when you download your PR from GitHub, they look like the left. There is also like a different diff format, like the line diff in the middle. Unfortunately, the canonical diff representations perform very poorly. So all the state-of-the-art coding, either agents or assistants or like anything basically out there that is capable of editing code in place, they end up creating their own bespoke format. So like the one on the right is coming up from one of the papers that we have been testing. There are a lot of different variations of them. You will see some diff formats that have XML tags. The reason why they do that is because we know that XML tags tend to work very well for LLMs when they want to structure the output. The shortcoming of doing this is, first of all, it requires a lot of trial and error because we're kind of coming up with a new format out of thin air. And the other one is token efficiency. Like diff representations, the standard ones, they're hyper optimized. And the reason is because like even something like GitHub, they want to have the most compact and concise representation. When you start to have like long XML tags, of course, you're burning tokens. Now for running small evals, it's totally fine. When you have a system in production in front of like hundreds of thousands of users or more, like every single token counts. So in the ideal world, eventually we're going to see LLMs capable of outputting proper diffs. We're not there yet. Hopefully someone in the industry hears this talk and makes me happy, but it's not the case still today. Last thing, and this is like basically one of the latest advancement in the field, is coming from Anthropic. And this was released back in end of October last year. So what they've done is, rather than basically, they started from what we were saying before, right? In this agentless architecture, you have an LLM call, and then you augment with information that comes from retrieving data, from calling tools, and maybe from memory management. But we can do something slightly smarter than this. We can fine-tune the model in post-training to learn how to use a specific tool that is specialized on searching and editing in place files. And that's exactly what Anthropic did. So they created a single tool that can view files based on the instruction that you pass it over, and then it can either create a new file in your code base or it could edit in place a specific file. And that's why the tool is called basically string replace. It has a few commands available, like it can also decide like to open a new file, it can execute commands, but it's very simple. The cool thing is that when you use it, the fact that it's been trained on so many samples on how to edit files, you're basically gonna be using it in distribution. Like it's meant to be used in this way. So it's very proficient at editing files. It's token efficient. It's very useful, especially for large files. The problem of large files that I was mentioning before is if you rewrite the entire file, it's gonna be very slow and also very expensive. Like output tokens tend to be much more expensive than input tokens. So in the ideal world, what you want is you have a view of the entire file, and then you have a tool that tells you these are the 3 lines of code that you have to change at position 10, 20, and 30. That is the most concise and cheap, basically, edit that you could be generating. It's one of the things that I recommend people to start from if they want to be like a coding agent quickly. Like it kind of solves a lot of the problems that we've been talking up until right now. But I'm bringing it up also to tell you that's where the industry seems to be heading towards right now. Like whenever you know that there is a very specific task that has certain requirements and a lot of people in the industry actually need to use it, it's much better to bring that intelligence within the model by means of creating a tool rather than building a lot of code around it as SWE-agent or even the first version of Replit Agent was released before this. So we built a lot of this logic in code rather than using it from the model. And we also talk about edit localization. So I'm going to give you a few pointers. We're not going to go in depth here, but there are additional things you could be doing with code. So imagine of a standard system that is doing RAG over a large corpus. If it's purely text, you kind of have like 2 tools in your tool belt. One is standard information retrieval techniques, TF, IDF, BM25, or you could be doing vector search. In the case of code, there are a few more things that could be attempted. Like first of all, you can list all the symbols that appear in your code. variables, method names, class names, and so forth. Usually, as a developer, you tend to look for those symbol names. You don't look for or while or like keywords that are going to be everywhere. You look for keywords that have higher discriminative power. So you can basically build a table of all the symbols appearing in your code base, and then you could search for, say, all the files where that specific method is being invoked. We also have tools like RipGraph that are very fast at scanning through a very large code base and like returning all the lines of code with specific mentions. And yes, last but not the least, of course, you can do vector search. I think if you want to look a bit of how to make the system scales, I recommend you to read the literature about binary embeddings. It's a very cheap way to implement vector search at scale, and the performance drop between doing, say, proper dense embeddings versus the truncated binary ones, the drop is so small that it's not worth anymore to use like old school embeddings. This is something that we learn at Replit, and we make it scale to the large code user base that we have by means of doing that. So happy to take more questions about it after. I know it's not very much agent related, but it's more to make you understand that when you want to actually make the system scales, it's not only about picking the best model and finding the couple of hard problems to solve. There is like a cascade effect of things that you need to optimize and make scale in order to make like the entire system affordable enough. Okay, so we went from the Agentless architecture, and now I'm going to give you like an intro about multi-agent architectures. Any questions about what we just talked about before we do another deep dive?
What's whatever was proposed before this RAG-based technique, like how far does that take you in the practical world?
Agentless, or what was done even before SWE-bench? I think it's super practical. And Cursor, Windsurf, they're all basically using variations of that. Like, I don't know all the details, but even if you do some level of peeking under the hood and seeing how their agent behave, they're all doing a variation of that. App building is a bit trickier than that, and that's basically what that's gonna be like the closing where I explain a bit how Replit Agent works, because it's not even like a different level of complexity, it's a different instantiation of how you build coding agents. Yeah.
Share a little more detail on the like bringing intelligence within the model versus building code around it. Like, what is sort of the distinction?
Will do. I'll get there. I have a build up to, and then ask me questions if I didn't make it clear, okay?
How large are these work that, like in terms of
in our case, they're not very big because most of the apps that people build on Replit are kind of like greenfield, 0 to 1. Sometimes they import all their smaller repositories, but they don't tend to be very large. And we don't index all the large tree of dependencies that they import. That problem is much more relevant when you end up in like an enterprise setting and you want to have an agent that runs on your code base. And there are places that have like billions and billions of lines of code. So in that case, indexing is not as trivial as even I was explaining before. Like even if you have a vector search over such a large code base, it's probably not a good idea to have a single index across the entirety of it. You probably want to split it per project or at least per programming language. So yeah, I think and a middle ground between these two extremes is local editors like Cursor, Windsurf, and so forth. They tend to work with usually larger code bases. And that's why you can ship your code to their servers and they're going to be doing indexing on the fly with their own embedding models. And then the search is not happening in local, it's happening on cloud. Yeah, but I would say that the largest ones that you realistically work with in local are, say, hundreds of thousands of tokens, give or take.
You see more this research happening in both like more towards like localization, like having to have a practical like localization, as opposed to RAG or searching over like large code bases or large knowledge bases?
I see papers. I wouldn't say there is enough going on there, unfortunately. And like maybe it's a recommendation if any of you wants to do research in this direction. Localization is a big problem. I think it's also a problem where as an independent researcher, you can actually have a lot of impact. Versus edits, it seems to have become a problem that model trainers want to solve, like for obvious reasons, like doing edits reliably is something that eventually the large frontier, models will have to solve. While localization is a problem that is always going to be offloaded to the agent builder.
We were talking about diff formats earlier. So you're just asking which diff format works best for the model, for the agent.
That's a great question. I don't know how much I want to answer for two reasons. The first of all is I don't think there is a proper, like there is not even like a paper out there with evals across a lot of different formats. I've only seen papers that describe one format and they show that it's better than the baseline. I haven't found a survey. It might be me not having found it yet. Usually survey papers take like a year plus before like a PhD student decides. The field is so wide and crowded that I need to write a survey paper. But they're all like variations of basically what I showed you. They are more verbose than a standard diff format, and they tend to have like block definitions that are much wider. And they don't rely on this syntax that usually like where a model gets lost. So they more rely on, it's very similar to say the structure output you see from all the LLM providers today. Like you define a schema and you say, okay, I expect this field to appear, this other field to appear, and that's how these bespoke diff formats look like. I wish I knew the answer, to be honest. And I also think that this is something that changes continuously. Like every time I try a new model with my team, we are kind of reinventing a bit of the format that works best for each one of them. So maybe another thing that I want to debunk is whenever you hear the AI pundits saying switching costs between model providers are very low, it couldn't be more false. Again, if you're building a chatbot, sure, probably true. You're actually building something as complicated as an agent where your control flow is decided by the LLM. There are so many things that go wrong just because your prompt is not optimized. And it takes a lot of time, especially because one thing is to have an eval like SWE-bench, which is very much downstream. So you rerun it, maybe you found out that you drop, say, 5 points. Then you have to go and dig deep to find out why that happened. Is it because my prompts are not optimized? Is it because, Gemini versus Sonnet expects a different output format? Like there are so many reasons. So that's another thing to keep in mind. Is not, you don't just switch model provider and things are magically better, unfortunately.
People use these benchmarks and then somehow get the model providers to come to consensus on the format.
You should give me the answer to that. We're working on benchmarking. Some of you are here today. I'm trying to create a benchmark bespoke for what we're doing in Replit Agent. It's an up-edge project going on. In general, I think I'm at this point old enough that I can complain about it. Coding benchmarks has always been subpar compared to the rest of the field. Like there's never been something as amazing as say MMLU or Big Bench for code. I think live code bench is kind of getting there, but it's still not exhaustive enough. I wouldn't be able to answer why. I don't know if it's because, I don't know. Maybe like coding became important only when research kind of stopped to be public, because that's what is going on. A lot of LLM research is not really public, so we don't know what's happening. Like maybe Anthropic and OpenAI know everything internally, and none of the alpha leaks out to us. But in general, benchmarks are not really there yet. The other challenge is like something like SWE-bench is very hard to create and set up and run. So like they become even more complicated it's hard to get excited a researcher to build something like SWE-bench. It's a lot of work, like a lot of engineering work as well. Well, I can see why. Anything else? Okay, that's good.
So on the switching costs, you mentioned between provider or like vendors or.
Yeah, even between models, by the way.
Models.
Yeah.
So even if you just stick with one vendor, you would still every 3, 6, whatever months face these switching costs because the way that.
Let me give you the most glaring example. Think of, you only use OpenAI and you decide to move from 4Omni to any reasoning model there now, like O1, O3, whatever is coming next based on some Altman tweet from a couple of days ago. You will have to change completely the way in which you express your prompts. Like reasoning models expect you to structure prompts in a different way. I think they call it don't do boomer prompts, which was like a very questionable marketing. Like they expect you to be much less verbose, and they expect you like to don't be too prescriptive with the reasoning model versus with a chat model, you keep using them as we are doing today.
If you take only reasoning models and you compare version 1 of one versus version 2 of that, or model 1 versus model 2 of the same vendor, you compare it to.
That is the least disruptive change that usually would have to go through because they tend to be incremental improvements.
So intra-vendor is less disruptive.
Intra-vendor is a bit better, yes. But like even intra-vendors, sometimes they decide maybe before structure output came out and became available with every vendor, each different vendor had a slightly different recommendation on how to try to induce structure in the output of the model. And now everyone tells you, use our structure output feature. But say you were building a product and you wanted to have optionality, you wanted to use 3 providers. Each one of them has a different implementation of structure output. Each one of them has a different implementation of prompt caching. And all in a sudden, your code base becomes far more complicated than it should be. It's like you're building software and you need to support different CPU architecture. That's what like cross-compiling solved, decades ago. It still remains a very painful problem. I feel we are kind of seeing exactly the same today,
It's going to converge.
Are you certain? I wish. I mean, of course, we all wish, but like the industry history will tell you otherwise, right? We didn't even manage to converge on CPU architectures. Like we had, x86 and ARM, and even if you were like an embedded engineer, you would wish, okay, at least metal is the same for everyone. And it's not the case. Or say AMD finally comes out with proper GPU support. They're not going to have CUDA. So people would have to reinvent their skill set from the ground up. I feel it's going to be similar here. Maybe it's not as painful. It's not like moving from CUDA to MLX. But yeah. No, I mean, everything is equally fun for me. But yeah, let's go through the multi-agent architectures. So in the ideal world, like when we wanted to build the simplest possible agent, we will just have a global context and a coherent trajectory. So what do I mean by that? You go to a React loop, you take an action, you put back the observation in context, and you keep looping. There is a practical limitation on why we can't use a global context. So first of all, and we finally reached one of my favorite plots, there is a poor long context understanding that LLMs are suffering today. This is a DeepMind paper from, I think, end of last year. You can Google it. It's called Michelangelo. And it shows you like the main takeaway is very simple. Even with toy problems, the performance degrades after you go past 2,000 tokens in context, and it drops even worse after 32K. So even if every vendor out there brags about the fact that they support 200,000 tokens in input, 1 million, 2 million, the truth is that is good enough to do needle in a haystack. Sometimes it's also good for multi-needle in a haystack. It doesn't mean that you can use the entirety of that context to just throw instructions and memories and logs from your agent and hope that the model will distill all that information and always make the right decision. To the extent that the more tokens you're using in input, the more weird behaviors you will be experiencing, such as the model doesn't choose to use the right tool or it doesn't output code. Like the more you go to the far right, the more unpredictable the behaviors of model become. So that kind of forces you to always keep kind of like a soft limit of how much your prompt can actually grow, which is far smaller than the allowed prompt size from the vendors. The other problem is how many tools actually models really support. Yes, in principle, if you read the recommendations, they tell you they definitely work well with tens of tools. In practice, especially for something like a coding agent where tools definitions are far from trivial. Like a tool is not, I'm going to call the API to check the temperature at Stanford. Tools are far more than that. You might be calling, you want to do like a shell execution with a lot of different flags. So there is a lot of complexity in each tool invocation. So it's not really true that you can put tons of tools in the scope and the model and the agent will always choose the right one. Also, in general, until basically now, most of the LLMs, even the frontier ones, they're not trained on agentic tasks. They were not meant to do that. They're mostly optimized for chatbots. And now that they realize that there is an amazing business opportunity in supporting agents, then we're seeing them putting more effort and basically doing more post-training for agentic tasks. But again, this is probably something we're going to be seeing in the following months. Last but not least, if we were doing this basic like global context and always calling the same model, there will be times where you will be using the smartest model out there to do something very trivial. And as you know, tokens cost quite a lot of money, especially if you're charging back your users for them. So having a different architecture where you can decide if a certain step should be taken with a chip like a Gemini Flash model versus like a Sonnet model, you see like an order of magnitude of difference or more.
Localization. So Catasta, you talked about comparing the current models, the generative models versus vector embeddings, which is cheaper. Of course, the embedding should be cheaper.
Much cheaper, yeah.
Which is better?
Unfortunately, generative models. Yeah, if you just wanna retrieve, then of course, like it's much cheaper to do that with vector search. And if you only care basically about recall, then vector search is enough. If you care about precision and especially like re-ranking, and say you have 50 candidates and you want to keep only the top 2 of them in context, no matter how smart you try to get with the re-ranking, the best re-ranking, of course, will come from a model that reads the code and tells you this snippet of code is the one related to your code base, and then select it. So I'm not going to have time to talk about this today, but there are this concept of single hop RAG versus multi-hop RAG, where if the task is easy enough, you probably rely only on vector search. If you find out that the agent is getting stuck, then you can decide to put more money. You throw more money to the problem, basically, and you put the code in context on an LLM. Yeah, great point. Okay, so this is the premise why we care about multi-agent architectures, in the sense that we take the high-level agent we talked about today, and then we factorize it into modes. And each mode has a different way to do context management. It has only a subset of the tools in scope, and it can also select which kind of model it needs. If you need the smartest model to do edits, you will be using Sonnet. If you need something that can just parse through a large amount of code, maybe you're going to be using Gemini Flash and so forth. So it gives you this kind of optionality. One example in the literature, just to show like how far this idea has been taken. One of the papers that we found is Codar, and they say we're going to see how a company works, and we're going to map that same architecture to a multi-agent. So they have a manager, they have basically product management, they have editors, they have verifiers, they have quality assurance engineers, and so forth. I think this maybe takes it too much to an extreme, but it's just to show you how wildly different were the 2 approaches we saw today, where Agentless is as trivial as it gets, and then this probably got a bit overcomplicated. But a good middle ground is something that you're seeing today also in some of the code editors, and also like Heather has been pioneering as well, is this combination of using a reasoning model to do planning, and then using model that is better suited to apply code edits. And in that case, it could be like a chat model such as Sonnet. So the idea here is you separate the two steps. Reasoning models, they seem to be doing extremely well at debugging code today. So they can take a lot of coding input. You can have a high level description of what is not working. And by means of reasoning and scaling test time compute, they usually do a much better job of any other model to pinpoint where the issue is. And then at least how things work today, you can take Sonnet and then go and edit the code in place and replace the few lines of code that are broken. Now, this separation is not going to be here likely forever. Like it might disappear very soon. If you read the OpenAI, I mean, it's not even a leak. Like Sam Altman tweeted about it a couple of days ago. He said GPT-5 will be a model where reasoning is optional. Like you could use it as a chat model, or you could use it as a reasoning model. We don't know the details. It could be like a discrete amount of reasoning modes, or it could be just a slider. But what matters here is there might be a model that unifies the two options that we're talking about, and that it allows you to become a good code editor when it's needed, or you could enable reasoning when you're trying to debug a problem, and then use it, in however way is most efficient. And by the way, it might disappear in a few months, but it could also reemerge later on, like depending on how the different labs make progress over time, there might always be a better model at reasoning, and there might be a better model at applying edits on the code. That's another challenge in actually building agents in the real world, where you're not really married to one model architecture and you think that it's going to last for the next 2-3 years. You need to be ready to refactor everything in a matter of like weeks if you want to always follow like the latest state of the art out there. It's a fun job. It can also get stressful, trust me. I'm talking from personal experience. So let's go. Let's talk about the basically beyond React, which is the question that you were asking me before. Like, how can we work more with a global context and do like basically more smooth reasoning? The issue is that if you hard code agent loops, as I just described it to you before, this might get in the way of the next generation of models. Basically, we are baking some priors when we decide exactly how a certain agentic loop should look like. So let me give an example. If you know that fixing that problem requires you searching code in a specific directory and maybe compiling that subdirectory and then applying a certain edit, that works if you know that your task is always exactly described in this way. But it turns out that it's also a very brittle architecture. And it would be much better if the model was just given the high-level intent that you have, and then it will decide, okay, these are the 4 different steps that I have to take. Until basically a few months ago, this optionality didn't exist. I do think that's exactly where we're going. So on the side of the agent builder, our task will be to decide like a high-level fixed prompt, so the instruction that we pass to the model, and we would have just to manage the context. So how much information we want to pass to the LLM. And then we will let the model just do smooth reasoning, and the model would have some tools available that will be defined directly by the vendor. So the model will have a tool to open a file, it will have a tool to invoke the shell, it will have a tool to do a string replace editor, we'll decide which actions to take, and then we will be basically keep calling the same model in a loop. This is what I believe will unlock like the next level of like power in terms of how good agents will be. And I expect that the agent scaffolds will become easier. At least that's also my hope. I think right now building agents, as maybe counterintuitive as it sounds, is probably 90% engineering. And it's very close to doing distributed systems. Like agents can fail in so many different ways, and you need to do like some level of defensive programming to make sure that things just don't explode, and that you always give a perception to the user that progress is actually being made. But it's extremely hard feat of engineering, rather than doing a lot of AI, which is probably what some people expect. So that being said, I don't think, again, I'm trying to show you what is the near-term future. I'm not saying what's going to happen when models will be at the level of AGI. It's more like, what is my prediction for the next year? I think we're going to be seeing more tools with specific interfaces, especially like for code use cases. And if you go and read the Anthropic blog post that I linked there, with something as simple as this, basically with the agent scaffold that they used was probably 100 lines of Python. They got 49% on SWE-bench, which is a very high score. It's very close still to today's state of the art. And the state of the art from Anthropic to where we are today is mostly accomplished by doing test time scaling. So this is just one single trajectory. It's just a series of calls in a loop. And if you want to get like this additional 10% that we've seen today, you need to spend orders of magnitude more tokens compared to what they did. So this is like a pretty remarkable result. And I think that's where we're going to be seeing the industry going towards too. Unfortunately, like I also want to highlight these shortcomings. The trajectories here tend to be very long and expensive. So if the model has to reason and decide, okay, these are the files that I should be opening, these are the edits that I should be making, it doesn't get everything right the first time. As in the model decide, okay, I'm going to start by editing these 2 files. And then it realizes it didn't do enough. And then it goes through a different iteration. And the model decides when to stop. So the way in which this is implemented, you put the tool in a while loop. It starts to execute. And then whenever there is a code that doesn't call any further tools, you know that the loop has ended. But you, as an agent builder, you have no control. So imagine exposing that in front of a user. Like you want to give them some expectation of how much a certain action will take, right? And the truth is, it's unbounded. So you can decide, of course, to hard code when it has to stop. Say, maybe I don't want to forward more than 10 calls to this tool, but the task might not have been accomplished by that. So in principle, it's very exciting. I think it is making us rethink how to build coding agents. In practice, actually, turn it into a product, it has some additional challenges.
Since I guess you can probably trajectories are like relaxing the previous agent framework.
Yeah.
How these new generating trajectories follow a different thinking pattern than previously defined.
Yeah, they do, because they are much smoother compared to you defining exactly how the React loop will look like. And they can make decisions on at each sub loop in this, let's call it routine. They decide which tools it should be calling. So you don't have any control. It's the model having full control across the entire trajectory of what you will be doing.
So success, actually were successful before. What are the reasoning patterns for yours?
For this one compared to other successful SWE-bench runs, the key difference here, these trajectories are longer because in a sense they're less optimized to be as concise as possible. If remember when we talk about Agentless, there is this split between locator and applying the edits. A lot of the logic and complexity is at the locator time, it's finding the right files. And this tool doesn't have that capability. It doesn't do vector search. It doesn't have a lot of complexity of doing the best possible locator. But it ends up finding the right files by looking at the directory structure. You literally pass a list of all the files available and the files, and then it decides which ones we use.
Previous frameworks don't have similar functions.
There are some results on SWE-bench at a similar level that definitely use fewer tokens than this. But I would argue that as an agent builder, this is much more elegant and we will require you much less effort to build and maintain. But then, yes, you will transfer that complexity from your engineers to your users. It will cost less to build an agent, but then it will be more expensive for the person who buys it, or it will be more expensive to run an evaluation. Yeah. I think like anything else that I've seen in AI, usually we extract the capability in some very ingenious ways, and then eventually there is always a trajectory to make them cheaper and more affordable. So at least as an insight is very powerful. And I think in the next few months, we're going to see how to actually everyone will put it in production. Okay, I think I should be moving fast because I have a few minutes left. Okay, this is where we're going to end. It's the last chapter. So we talk a lot about, if you think about it, creating PRs. So we are starting from projects for which some code base is already available. Then there is an engineer who described an issue that the code base has, and then our agent goes ahead and tries to locate the right files and applies edit. Then we talk about different strategies on how that can happen. The truth is there are many other things that you do as a software developer. You don't only do PRs, and especially when you try to build things 0 to 1, your effort is completely different compared to landing in a pre-existing code base and finding which small parts of it you should be editing. So, and this is literally something that's been happening a lot in the last few months. There are a few other benchmarks out there where we have been testing models head-to-head on generating, let's say, UIs from scratch. So one of them is under the LM-sys umbrella. I'm sure you heard about LM-sys. Probably web dev arena is still not that notable, but the idea is you do go there, you write a prompt. In this case, I wrote build me a Twitter clone, And then there are two models in parallel that are trying to generate that interface. And then the arena is asking you to rank which one of the two you prefer. And that's how you're going to end up basically getting the ELO score. And now it shouldn't come as a surprise, but all the models that are on top on the leaderboard today are Sonnet 3.5. If you ever use Claude AI, I'm sure that you try the artifact feature that they have, where sometimes, depending on what you write in the prompt, they build a small web app on the fly for you. Why are they so good at that? Because they're basically capable at this task. The model has been post-trained. The model has been post-trained on a lot of examples of how to build small web applications end-to-end. And that's why it becomes so proficient at this task. Another one that is also getting some attention is the SWE arena. It extends the chatbot arena. It's like very famous with code execution. And again, it comes up with an ELO score. Basically, it generates code on the fly. Rather than being simply a web application, it can run a bit more a variety of different programming languages. But the concept is exactly the same. Like, can we take a simple LLM and with a single shot prompt, can we generate an application end-to-end? The reason why I'm excited about this is because this is one of the core principles of what we use to build Replit Agent. So I don't know how many of you will know about Replit and us as a company and as a product, but the mission that we have is to democratize software creation. Like, I want to see 1 billion people eventually becoming software creators. And we're going to accomplish that not by making writing code easier, because that's the barrier of entry to that is still very high. We're doing that rather by, nice dog. We're doing that rather by allowing people to create software just by specifying their intent in natural language, and then the agent builds everything under the hood. And one of the insights that we use to build Replit Agent is the following. We think of it as a composition of what I just showed you and what we talked about basically for the first hour today. There is an initial phase where we try to rapidly generate a working application. And maybe we bring in a stack choice. So you could be building a JavaScript app, you could be building a Python script. So you go through the process of selecting what you want. And the first goal that we have is the application we build must run, must look good, like it must have a nice user experience. And the moment you do that and you make it happen, say in a couple of minutes, you really capture the attention of the user. And a lot of non-engineers out there, they desperately need tools like this one. If you're a designer, rather than spending a lot of time on Figma drawing your UI, you could try to generate it with an agent and basically put it in front of your colleagues or your customers. And similarly, if you can build an internal tool very quickly, a lot of people basically would start to create software. Now, the catch here is if you stop just at this, the scope of what you will be building will be very narrow, right? You're just building like a basic web application. So with Replit Agent, we compose these two concepts. We first go to prototype as quickly as possible, and then we attach an agent that works similar to what we discussed about, where you can iteratively add new features to the app. And just to make things different compared to what I told you before, we keep the human in the loop during the process. And keeping the human in the loop is not purely like a product choice so that it's less boring and we get more user engagement. Of course, it plays a role. Like, don't get me wrong. I think it was like a very good insight to keep the user there and keep them excited. But the truth is, and this is the last takeaway that I want you to have from today's lecture, the main complexity of agents is that their reliability drops dramatically over time. I keep saying that regarding the context, but in general, the more steps are required for an agent to accomplish a task, the faster the probability goes to zero that it's going to be successful. That's basically like compounding errors. What is the easiest way to avoid compounding errors? Is not making the best agent in the market, because the truth is that's a pipe dream that is going to require, who knows, months, years, decades. The way to take a shortcut is by having the user in the loop, so that after a few steps, you can ask the user, is this what you wanted? What is broken? Can you try the application for us and tell us what's wrong? And you could think of that purely as a debug job that we are outsourcing to the human. It's more subtle than that. A lot of people, including myself, we don't know how to write specifications of the software we want to build. there is a reason why companies have software engineers and product management and a lot of different roles. Like there is always a discourse going on between people that have clarity on what they want to build and people that know how to build things. So we launched Replit Agent 5 months ago, and every now and then I go through the data of all the different prompts that people submit. And it's fascinating. It's like the most fascinating data set I ever put my hands on, because the variance of what people write as the initial prompt is absolutely wild. It goes from single one-liners, very generic, and a lot of people maybe sometimes they write feedback and they say, I want you to build a Twitter clone, and if it's not exactly as powerful as Twitter, they're very much disappointed. Some others are excited even if the UI is kind of there. So even the expectations are not set yet. I think we went from 2 years ago, a bit more than 2 years ago, people not even knowing what a chatbot was. And now the expectation is, oh, it's a coding agent. It has to build everything on the spot. Some others instead are writing very long descriptions of exactly what they want. And even there, it's very hard for an agent to take like 2 pages of markdown and turn it into something functioning on the spot. So, and that's the reason why having a human in the loop allows us to prime them to splitting the task into several subtasks so that they can ask us things in a sequence, and then they can see the application being built as we go. Before we go,